Okay, so in project 3, we were talking about the monostable mode of a 555 timer used to debounce a switch. So this is the circuit that we have all been using, 555 timer IC based switch debouncer. And just to give you a quick recap of what this was supposed to do, your switch was connected to pin 2, and if this was a bouncy switch, which most real switches are bouncy, so the transition from one level to the other level is not clean and it tends to bounce for a few milliseconds, and depending on how what type of switch it is, those times may vary. So if you have that bouncy switch, it might trigger some events that are not desirable. So in that case, what you can do is we can use a 555 timer and essentially charge a capacitor to a certain value and then discharge it only once, meaning when the switch is pressed, it gets charged and then discharged to give you an output pulse, which is a square pulse, as opposed to a bouncy pulse. But that is happening only once. So because we are operating this in a monostable mode, we are just getting one clean pulse, as opposed to in the astable mode where we got a free running pulses. We are using a pull-up resistor to connect the output of pin 2 to high, and by doing that we achieve a waveform at pin 2. So if I will highlight pin 2, the waveform at pin 2 now looks like this. So you have your time axis here, say this is your voltage on pin 2. It would look something like this. It would be, so if the switch is not pressed, then pin 2 will read high because it is not connected to ground through the switch. So it will be high there. And then when somebody presses the switch, then it will go down for a few moments and then it will come back up because the switch is released. Now during that process, you might have glitches over here, which means that it goes up and down, um, having that bounce. So let me highlight that. This is going to be 0 here. This is going to be, say, high, close to 5 volts. So we start charging the capacitor when the voltage on pin 2 is going to go below 1/3 of 5 volts. And it is that because pin 2 is connected to the trigger comparator, which is the bottom op amp inside the 555 IC, and the threshold voltage to that is 1/3 of the VCC, and we talked about that in the several times in the previous lectures. So the moment it goes below 1/3 VCC, so this is 5 divided by 3, it goes below 1/3 VCC, we are going to start charging up the capacitor. So if I monitor the charge on the capacitor just over here, you are going to have no charge, and then the moment it goes below 1/3 VCC, it's going to start charging up. Now, until when it will it'll charge up? Well, if you look at this, the capacitor, which is getting charged up, in this case C1, is connected to pin 7, which is the discharge pin, and is also connected to pin 6, which is the uh, threshold comparator input. And the threshold is being compared to 2/3 VCC, and over here it's 1/3 VCC. So the capacitor will charge until the capacitor voltage reaches 2/3 of that voltage. So let me draw that over here. This is going to be still voltage, and this is the voltage across the capacitor. This is again time. So once it reaches 2/3 of VCC, it is going to uh, flip the comparator output, the threshold comparator output, and you're going to start discharging the capacitor through pin 7, which will lead to an instant discharge. Now, all of this will result in an output pin going 0 here, and then it'll jump high and it'll stay high, and then it'll come back over down over there. So highlighted in blue is pin 3, which is the output that we desire. So as you can see here, we pressed this button only for a short duration of time, but because we were charging a capacitor through a resistor slowly, we had a time constant, and only when it reached 2/3 of the VCC, it was allowed to discharge. So that gave us that clean pulse. So that's the operation of this switch debouncer that we have been considering. And to do this, we have been using an equation of 1.1 times R1 and C1, which is essentially related to this, right? So it is answering the question, how long does it take for the capacitor to go from 0 to 2/3 of VCC? And because we have seen the charge and discharge equations of the capacitor, we know how to calculate that. So we have done this before. In the last class, we did this. The time uh, d over here is for duration of time, the pulse. So the time duration of that pulse observed on pin 3 of the 555 timer is in an equation 1.1 times R1 and C1. And if we choose R1 to be 100 kilo ohms, then we can obtain any desired duration, say for example 100 milliseconds in our case. For that, we would have to pick a certain C1. And if you do go through this calculation of desired duration is over 100 millisecond, we have 100K for R1, that C1 will come out to be a value of close to 1 microfarad. Um, and we have done that experiment in the previous class where we used the R1 as 100K and C1 as 1 microfarad run through the experiment. And we have seen that the fake switch at least was getting debounced. Then we applied that to a counter to trigger it. When we applied that to a realistic scenario, we saw that 1 microfarad wasn't enough and we had to actually increase it a little bit. So we went to 2 microfarad and then everything was good. So that's what we did in the last class. Now today, apart from answering your question about how to do this in Pspice, I'm also going to talk about one more important aspect of this, which is, right, where is my page? There. So we have kind of done 1, 2, 3, 4. I'm going to talk about how do you improve the energy consumption. That's what we had reserved for today. So let's answer that question about how do you simulate this bouncy switch in Pspice. So if I zoom in on, this is page 2 of project 3 writer, and let me erase this so that you get clarity. So there are 5 voltage pulses that you use. In capture, you would have to use the part V pulse. So there are 5 of them, and there is a polarity to this. So of course, there is, to any voltage source there is a positive and negative terminal. And if I zoom in over here, I can see that the V5 voltage pulse that is shown has a polarity of positive on this side and negative on this side. Because of how this is, negative there indicated by negative sign, and then the pulse comes in and that is indicated by the positive sign here. And that is the same for each one of the 5 supplies. All of those combined, connected back to back, that is what is simulating the bouncy switch. Because if you put all these voltage switches onto a blank schematic, enter all these values for time delay, time duration, no, this is time delay, right? Time delay, fall time, pulse width, period, high voltage, low voltage, rise time. So you have rise time, fall time, pulse width, period, and delay. If you enter all these 6 values, 7 values for each one of the 5 sources, accurately as per what is given, you will see if you probe that voltage supply from end to end, meaning you put one probe over here and you put the against the ground terminal, if you measure that voltage, you should see whatever you see in the red. So by using those numbers, we have made sure that our voltage supply does that bouncy nature. So all of that should be going into pin 2 because that is what is simulating the bouncy switch. So how do I connect that to pin 2? Well, I'll have 5 sources over here, and I will take the top of all these sources and I will go into pin 2 of my debouncer circuit. And this of course is connected to ground, so that's okay. That's independent. So how do I go into pin 2 from there? Well, if you see this diagram, all I would do is I would remove the bouncy switch from here, S1, and at pin 2, I would connect the 5 voltage sources, and the other side of those 5 voltage sources is connected to ground. All the others will, well, I would not put this resistor 10K, so it is not present. This R2 is not to be included in capture Pspice. Now, if you're wondering why that R2 is not included in um, capture Pspice, it is also not included when we do the fake data bounce. So why is it not included? Because R2 allows us to get a waveform that goes from high to low, to get it that in that particular form. When you press that switch, it goes from high to low, and we need that because that is the only way we go lower than 1/3 of the supply voltage. So if we are somehow able to manage a pin to voltage like that, going from high to low and coming back up high without using R2, then we don't need R2. So for example, over here, as you can see, the red guy, which is the bouncy switch, it is also already doing that. So without even the uh, pull-up resistor, it is doing that. So in that case, you would not include the pull-up resistor. The same thing applies for the fake bounce switch that we did. Okay, so how about the rest of the circuit that goes inside the debouncer circuit? Well, it includes R1, C1, C2, the 555 timer. Sorry, the pull-up resistor is not there. There's no pull-up resistor there. And then the output of that debouncer, which is the pin 3 voltage, that you would measure using another scope or another voltage marker. So when you do that, you should see a blue, the blue output pulse that is highlighted on this diagram. If you choose your components correctly. Those components right now are 100K and 1 microfarad, leading to a time duration of the pulse to be about 110 milliseconds. This is of course theoretical. Your practical results might be slightly different. And as you can see here, the blue guy stays on for around that time, 110 milliseconds. Okay, so I hope that answers your question about the bouncy switch. Are there other questions at this point about the simulation, about the design equations? Because now we can move on to improving the energy performance. So Justin says, I'm generally confused about the system design portion of project 3. Are we supposed to just analyze the outputs at different pins? Um, we are supposed to monitor. Um, so let's see. If I go back over here, the design is very limited because it is just based off of these equations. So it's not like 10 different equations that you're putting together. The design is basically for how long do you want that switch to stay on. And there are a few things that you need to consider in a realistic scenario when you do that. So, for example, if I look at this, right, say I erase these two things and I say, okay, don't come back down just here, right here. Don't do that. Instead, stay on for a few more milliseconds and come back down over here. If I did that, what is the problem? The problem is that during this time window, what is that? 400 to 560. So that's a 160 millisecond time window in which another press on that button will be ignored. So I will not get another pulse over there in during that time because the capacitor is going to continue charging over that period of time. So every press will be that long, right? And what we are doing over here is we are essentially saying, okay, how do you I pick R1 and how do I pick C1? In terms of design, those are your choices that you are trying to make. Um, so there is not too many aspects to project 3, and I've been you know informing you about that from the beginning. There are not too many things to do. In fact, for the students, it is going to be about Pspice simulation. And in Pspice, how do you simulate the bouncy switch? And that was the question that we just talked about. How do I check the input? How do I check the output? And also, we are going to do some power calculations in Pspice. So hang on to that. Uh, are we just analyzing the outputs at different pins? Well, you are analyzing the output and pin 2. You are analyzing output at and pin 3. So pin 2 and pin 3 are the most crucial. And if you are interested in looking at voltages at pin 6 or 7, well, you can do that as well, which should look like 0, charges up to 2/3, goes back down, and so on. So the one that is highlighted in red in this plot. So yes, you can look at pin 2, 3, 6, and 7 together. Apart from that, you have 8 and 1, 8, 4, 1. Those are all connected to either voltage supply or ground. So those are constant. So in terms of analysis, let me see. Let me just write that down for your reference. Uh, pin 3, pin 2, and pin 6, 7, they are both connected together. So in the analog discovery plots that I'm providing, I just have pin 2 and pin 3. Pin 6 and pin 7 I don't have. The two scopes that I am using, I'm using them for pin 2 and 3. I hope that answers your question a little bit. Hopefully, when you see the power calculations, you will see, okay, there is a little bit more design involved in this, which we are getting to in just a bit. Other questions? Okay, so it looks like you guys don't have questions at the moment. So we'll continue talking about uh, the energy consumption. So, how do I look at improving the energy consumption of this 555 timer? So, it is again based off of the same equations. So, what I'll do is I will add another slide here and I will say the design equation was what? TD is 1.1 times R1 times C1. So, right now, what we did was in circuit 1, or the circuit that we looked at in the last class and we have been talking about so far, that is circuit 1. And circuit 1, we had R1 to be 100K and C1 to be 1 microfarad, so that our time duration of the pulse was about 110 milliseconds, and that is the theoretical value. Now for circuit 2, my goal is going to be to have a variation of this debouncer circuit so that I still debounce the switch. So I want to continue debouncing the switch. So still the same goal, which means my TD ideally should be about the same theoretically, but I need a new circuit. So what I'm going to do is this. I'm going to pick a value of 10K for R1 and I'm going to proportionally increase C1 to 10 microfarad. And as you can see, the product times 1.1 over here is 110 and over here as well is 110. So all I did was rearrange the product to have two different components for R1 and C1, which made the circuit behave slightly differently when it comes to the power consumption. And that's our goal. So the first question would be, which one consumes less power? Which circuit consumes less power on average? Well, I know that if the resistor is high, it is going to draw limited small amount of current from the supply. So the power consumption over here in circuit 1 is going to be smaller on average than circuit 2. So my answer, my estimated or expected answer is going to be so which consumes less. Circuit 1 should consume less power. The reason is there's a higher resistor there, which means that it's going to draw a smaller amount of current from the voltage supply. And if you look back at this diagram here, you have all these components. Which what are we monitoring in terms of power consumption? Whose power consumption are we monitoring? Well, we are trying to monitor the power consumption of that guy right there, the voltage supply itself. All the others are going to be uh, you know uh, irrelevant. The voltage supply is what is supplying power to all the circuit. So that's what we are trying to monitor. That's with respect to the power supply, also called as VCC in our discussion. Okay, so I hope that you have now some background about what our two circuits are going to be and how that power relates to that, when which circuit is expected to use lesser power. Now, uh, what I will do is I have simulated this in Pspice, but I don't want to share my Pspice simulation with you entirely. I want to leave that to you to figure out. However, I can show you how I monitored average power consumption in Pspice. It is very difficult to do that in analog discovery because I'm trying to look at how much current is coming out of the red power supply. So I would have to put a current sensing resistor in front of it, monitor the current that flows through the resistor, and then do that power calculation as an average. So that's a little bit of a tedious task. I'm not going to do that. Instead, I'm going to do the power calculation in Pspice. And all of that is being done to answer this question: which circuit consumes less power, right? So I'm going to do a Pspice simulation to also answer this question. Right now, I know what to expect. So I'm going to validate that answer now. So let's see. I've put up this circuit and say so I'm going to share my Pspice results window with you so that you can see that. Um, Give me one moment while my program runs and I get the window. Okay, so um, when I have voltage markers on the bouncy switch and the not bouncy switch, trace property, I'm going to make this slightly thicker so that you can see it very clearly. Right, and this is my bouncy switch. Right. Um, a couple of things to note over here. You have to provide a small enough time step so that you see the waveform as it is supposed to be seen. For example, if you have a big time step while you're running the simulation, you might miss all of this up and down aspect, the bouncy aspect. So make sure that you have a small enough uh, time step. So we are in project 3, we are asked to run this simulation from 300 millisecond to 600 millisecond. So I ran the simulation for 600 millisecond, but I started saving data from 300 millisecond. And I believe my simulation step size was about 1 microsecond. Let me quickly check here if I can look at the properties. So 0.01 millisecond. So 10 microsecond was my time step. So please make sure that you choose a small enough time step so that you have enough time precision, or I should say granularity, to be able to monitor that waveform. Okay, so I will say okay of this and then come out. So that is what I obtained in terms of input and output. So this is what we have been discussing so far. So now the question is, how do I monitor average power in Pspice? So what I'm going to do is I'm going to well, I can delete these two traces. So I don't need them anymore. I will delete this. I will delete this. I have a blank window. I will right click and I will say add trace. And when I select add trace, on the left here I have the option to select any one of the output variables. I can select multiple of them, I can select one of them. It's my choice. So what I'll do is I will select V1. And the reason why I selected V1 is because that is my voltage, DC voltage source in my schematic. The others are the other voltage sources are uh, essentially faking the switch, the bouncy switch. So V1 is my DC power supply, and W, which stands for wattage, which is going to give me the instantaneous power that is supplied by this voltage source. So W for power, V1 for the component that we are monitoring, and I'll say OK. So when I say OK, let me actually change the color here. Uh, Perhaps red, and slightly make it thicker. Yeah. So as you can see here, this is uh, power consumption as a function of time. The x-axis is time, and as you can see, when we didn't press the switch, the power consumption was about there. So if I zoom in, I can find out what that value was. So it was around negative 2.6 milliwatts. So the question is, why is it negative? The reason why it is negative is because it is talking about the power that is being supplied as opposed to power being absorbed. So because it is supplying the power, it is in a negative sign. So what actually we can do is, to avoid confusion, we can go into the trace and actually make it negative, right? Negative, and say okay. So now you can see what that negative is going to be. So this is essentially power being supplied by the uh, DC source. Earlier, when we didn't have the negative sign for this voltage waveform, it was power being absorbed by that voltage source, which is why it was negative. So let's go and take a look at what these average values are going to be. If I zoom in on this, it is 2.6 milliwatts, and when I press the button, the power changes a bit, and the average over here during this period is around 2 milliwatts, and over here at the very end, when I release the switch, again it comes back to 2.6 milliwatts. So as you can see, the average power consumption of my circuit when I use 10 kilo, and all of these are for 10 kilo ohm. This is circuit 2. 10 kilo ohm and 10 microfarad is going to be 2.6 milliwatts. So what you would do is you would have another simulation in which you will use the 100K and the 1 microfarad capacitor, run a similar simulation, look at the average. So you're averaging it for the same amount of time, say 300 milliseconds. Most of the time is being when spent when the power is, when the switch is not being pressed, but there is a 110 milliseconds time window during which the switch is actually being pressed. Um, and because that capacitor is charging, you see that power transition from one value to the other. It changes because the capacitor is charging during that time, from 0 to 2/3 VCC. um, I hope I have given you a good idea about how to monitor average power consumption in Pspice very quickly. Just go to your just start up a simulation profile and add a trace which monitors power of the supply voltage. Note that this is not going to be for all those V pulse bouncy switch related voltage supplies. This is only going to be for the DC power supply, the power supply of the entire design. We are trying to monitor the power for that. And now in my case it was V1. Okay. um, so what I am going to do now is bring my window back here, close it out. Actually, I'll leave it here, and I'll take your questions now. So about circuit 1, circuit 2, how we are um, calculating the average power consumption of each of those circuits in PSpice. How do we know that circuit 1 consumes less power? Because I wrote this based on my expectation of a smaller resistor versus a bigger resistor. You can of course validate that using the exercise that we just did in PSpice. Um, okay, I guess I can take your questions now. I still can't find the button. Uh, Jason, the button. Okay, the button is this. This is the button. So this is the fake button. So all of that needs to go into your, wherever you have your bouncy switch, all of that needs to go over there. So this is where your 5 V pulse voltage sources are going to go. That's how we are simulating a bouncy switch. Yes, ignore the pull up resistor. That's exactly right. The debouncer is the 555 circuit. Yes, it is the circuit. So let's see. Let me highlight the debouncer circuit here. It is this guy. It is also this guy. It is also this guy. It is all those connections. It is also this guy. All of that. So no, I'm going to draw this. So that is my debouncer circuit. I'm going to ignore this. C2 is a capacitor used for controlling the voltage of the threshold capacitor. So instead of having that change based on two-thirds VCC, we can change that. But for the purposes of EI, we are not going to use the control voltage. So essentially, if for example, you say if you wanted to sample a signal, um, so you wanted to convert a signal into a pulse width modulated signal, you could apply that to pin 5. So that is um, that is a little bit beyond the scope of this class. No problem. Who has a question next? So we talked about power, we talked about two circuits, we talked about how to monitor power consumption in Pspice, which is typically where most people get confused. Um, and just to give you guys an idea about what's going on, because I am your partner that is working on all the experiments. So as a good partner, I have been doing the experiments and I have been uploading them onto the Piazza uh, resources page for project 3. And so far I believe I have uploaded most things. A couple of things are just missing. I will do that as well. So let's see. Going to bring in my Piazza window here. uh, then let's see, resources, and so project 3 results are at the top here. There is a circuit schematic that I'm using. There are a few images of the board that I built. Then I've been uploading what is the fake bounce custom data that we generated using WaveGen. How did it get debounced? How does the pin 7 look like for the fake switch? Fake switch again, pin 2 versus pin 3, and then the real switch for pin 3. Um, Now, today I'm going to look at the um, real switch with, not the real switch, sorry, I will look at circuit 2. So I'll change those values from 10k to 100k to 10k, and I will change C1 from 1 microfarad to 10 microfarad, and do that same experiment again. So I don't think there is any point showing you guys how to do that. There's just a simple uh, component swap and run the experiment. So I'll just upload those results. Okay, so what I will do now is I will stop the recording and I will take your